All right, so this is Monday's lecture. So parametric equations and calculus continued. We're only going to do the front of these notes. So on the back, I might briefly show you how to do an integral of a parametric function, but that is not an actual standard in the AP test, so they're not going to ask you about that. And we're just going to cut it because it's not that big of a deal right now. But what they will totally ask you to do is to find a higher order parametric derivative, so a second derivative. The third derivative process would follow the same idea. They're not going to ask you to find a third derivative either, but they will ask you to find a second derivative, and therefore they will ask you to discuss the concavity of a parametric function. All right, so on Monday, or Friday, whenever I last saw you, we talked about how to find the derivative of a parametric. So we looked at the derivative of a parametric, remember, is dy dx equals dy dt over dx dt, the change in y over the change in x. So parametrics are weird because when I'm taking these derivatives and I'm writing these tangent lines, I'm writing them in the xy plane, and my input variables are x's. But the parametrically defined functions, their input variables are time. So there's something tricky that you have to do when you take a higher order derivative. So when I take a derivative of dy dx, so d dx of dy dx, so I'm taking a derivative with respect to x here, of dy dx. So when you do that parametrically, though, what's going on is my inputs for dy dx are time. And you can't see that when you're written as dy dx, but the input is t. So when I do d dx, what I really have to think about is d dt dx, because I have to take a derivative to time, and what I see here is d dx. Now, it's really strange. Don't worry too much about the y and the meticulous things in there with this, but what you do need to remember is when you take a second derivative, you have to just take the derivative of dy dx that you've already found, but you have to adjust it by dividing by dx dt again. What that is when you multiply by the dt dx, when you're taking a derivative of this first derivative, well, multiplying by dt dx is the same thing as dividing on the bottom by dx dt. Okay, so you have to kind of adjust. It's a little weird. Let me show you. So, for example 1, it says for the curve given by x equals the square root of t, and y is this, t is positive. T has to be positive because it's the square root of t, so you can't take negative square roots. Square roots of negative numbers. So it says find the slope and concavity at a point. All right, so let's look at this picture. So what we have, it's pretty bland, but I'm trying to find the slope and the concavity at the point 2, 3. Slope and concavity at that point. All right, well, to find the slope at the point, so what I need is t. Remember, t is controlling these things. So if x is 2 and y is 3, well, say 2 equals the square root of t, and 3 equals 1/4 t squared minus 4, and then solve both of those. So t is plus or minus 4. And t is 4, so the overlap, we're going to take t equaling 4. T can't be negative 4 because that would be an imaginary number. All right, so time is 4. So that's going to make our finishing of the slope and concavities easier. So if I need the slope, the next thing I need is dy dx. So dy dx is dy dt. Write it every time. I know it's annoying. Over dx dt. But that's a point on the AP test, even if you screw up the derivative. So the derivative of y goes on top. So the coefficient 1/4 sits there. 2t. On the bottom, remember that's t to the 1/2. So I got 1/2 t to the negative 1/2. Then I might go simplify all of this. Let's see, I wound up getting 1/2 t over, you could write this as 1 over t to the 1/2 on the bottom. If you wanted to write that as t over 2, outside inside, you get t to the 3/2 over 2. Wait, that was 2 as well. So it's just t to the 3/2. I'm going to make some mistakes the next few weeks, and there's no way for me to go backwards. I'm sorry. It's going to happen. All right, so my first derivative is t to the 3/2. Okay, so I know that dy, let me rewrite that. So dy dx equals t to the 3/2. All right, so if I wanted to find the slope, I can quickly find the slope right now. So dy dx such that t equals 4, well, it's just 4 to the 3/2. So remember, the root goes on the bottom. So it's square root of 4 cubed. Do the root first, so that's 2 cubed, which is 8. So the slope is 8. So you have the slope, and you have the point. You could quickly write the tangent line. That could be a question. The slope of 8 makes sense here. It's a pretty steep slope at that green dot. So you could get off the train right here, if you will, and go ahead and write a tangent line, but that wasn't what the question was. Find the slope and find the concavity. All right, so to find the concavity, you need the second derivative. So to find the second derivative, d squared y dx squared. So you take the derivative of dy dx, so the derivative of the first derivative, but you have to also chain it and divide by dx dt again. So remember, we have found dx dt already, so dx dt is over here. So we already know what dx dt is. So the derivative at the top is 3/2 t to the 1/2, and then dx dt is 1 over 2 t to the negative 1/2. So there's my second derivative. It's a little bit of a mess, but it actually cleans up really nice. So 3/2 divided by 1/2 is just 3, and then t to the 1/2 divided by t to the negative 1/2 is just t. So the second derivative is just 3t. So if I want the second derivative such that t equals 4, you get 12. So that means it's concave up, which, looking at this picture, we can see concave up like a cup. It agrees. You won't have an image on the AP test of what the functions actually look like, but that's the process. All right, next one. So it says, for the curve given parametrically, identify the intervals of increase and decrease. All right, so a function is increasing where its derivative is positive, okay, and then a function is decreasing where its derivative is negative. Start with intervals of increase and decrease. I'm going to draw a little line down the middle of my page. Two different questions here. So I need dy dx. So dy dt, write it every time, over dx dt. So dy dt is 3t squared minus 3. dx dt is 2t. All right, so identify intervals of increase and decrease. So this is the first derivative test. So remember, we did this way back when. So we make a sign chart. This is my first derivative sign chart. All right, I'm looking for critical values. So I got where the top and the bottom equals 0. So critical value of 0. If you set the top equal to 0, get plus or minus 1. Remember, those are t values. All right, so now I'm just going to plug in intermediate points. So if I plug in 100, I get a positive. If I plug in 1/2, so I get 3 times a fourth minus 3, which is negative, over a positive, which is negative. If I plug in negative a half, I get a negative over a negative, which is a positive. If I plug in negative 1,000, I get a negative. And I'm going fast because there's a time limit on my uploading. So pause the video and go back and plug these things in and make sure you agree with me with this. So what I'm seeing here is this function is decreasing when negative infinity to negative 1 and 0 to 1. And it's increasing when the derivative is positive, which is negative 1 to 0 and 1 to infinity. I would really advise you to go and graph this in your graphing calculator. I don't have a way to show you that from the TI perspective here, but as you graph it, we might can let's see, so let's just look at, I guess, where it said it's increasing. It said it's increasing from negative 1 to 0. So this is that's the weird thing. So it's starting at the top. So what it's claiming here is that I'm increasing while the function is doing this. So that's considering increasing. Now the reason that, and that's a little weird, but remember there's two movements here. So this thing is moving left and moving down. So my slope is the down movement over the left movement. So it's a negative over a negative, which is a resultant of a positive. So where dx, or where y dt and dx dt are both negative, means that the overall slope is positive. So that's a little strange. So the two types of movements that are considered a positive slope are this or this. And then the two types of movements that are considered a negative slope would be if one of the dy dt or the dx dt is negative. So that's considered a positive movement. But when I get to 0 and I move to 1, that's a negative slope because you're going down and to the right. So it's negative over positive. Whereas, let's see it again. So negative 1 to 0 is considered a positive slope because it's negative over negative, which is a positive. So it makes more sense, honestly, just straight up algebraically than it does sometimes when you look at the picture, because that seems a little counterintuitive. But left and down is a positive slope, whereas and right and up is a positive slope. And the reason is because when you're looking at these, you're talking about, if I were to draw a tangent line on this thing, the tangent line is what's positive. So you got to kind of separate yourself from the movement parametrically. And now you're thinking about, so this thing we're saying is a positive slope. Well, yeah, because the tangent line to that point is positive. That's kind of what you're looking at. All right, I also want to know where it's concave up and down. So that's a second derivative. All right, so I need the d squared y dx squared. So you're going to take another derivative of the first derivative, which we've already found, and you're going to divide that by dx dt. Okay, so the derivative I already have is a quotient rule, so it's the derivative that I'm working from right here. So the derivative at the top times the bottom minus the derivative of the bottom times the top. All over the bottom squared. Don't mess that up. A lot of people will put 2t squared, but it's, you gotta square the 2 and the t. So that's the derivative of the top, and you gotta divide that by dx dt, which is just 2t. So my second derivative, and I want to clean this up, 12t squared minus 6t squared plus 6 all over 6t cubed, which is just 6t squared, let's see, plus 1, divided by 8t cubed. That's an 8, sorry. So there's my second derivative. So the only solutions to that, I got plus or minus -1 square root, which is imaginary, and then I have 0 is the solution at the bottom. So my second derivative sign chart has a 0 on it. So if I plug in 100 there, you get a positive, or positive is positive. And plug in like -4, you get a negative. So I'm concave up from 0 to infinity, concave down from -infinity to 0, which I can see. So remove your movement in your mind, but I'm concave up from 0 to infinity. That's all concave up. It looks like, I agree. And then concave down everywhere else. All right, that's all you got to worry about. The back, not really a huge deal. If you are interested in it, you can go look at it. So you don't have to find area of parametric curves. We will do a lot of area of polar curves. The key is you got to do it all in terms of theta. So when it says evaluate this thing, so the thing to remember is that those are terms of x. So your limits are x values here. So when I rewrite this, it's all going to be in terms of theta. So y is 2 cosine theta. So that's what y is. If you listen closely, you can hear my baby crying in the background. And then dx, so if x is 2 cosine theta, dx is 2, sorry, if x is 2 sine theta, dx is 2 cosine theta. So dx is 2 cosine theta d theta. So dx is all of that. And then my limits, these are x's, so you gotta go over here. So if 2 equals 2 equals 2 sine theta. So sine theta equals 1. So then you gotta know your limits for inverse trig, and we got an upper limit of pi over 2. And then -2 equals 2 sine theta. So -1 is sine theta. So where is sine -1? Which is going to be 3 pi over 2. Okay, go negative pi over 2. So now we got 4 integral 3 pi over 2 to pi over 2 of cosine squared theta d theta. Now it's all in terms of theta, and now it's an easy integral from the past. But don't worry about the back, not a big deal. The front. All right, I've added what you should do now. I've added in the drive for today a worksheet with some really good questions here. If it'll load. All right, so 1 through 5 are just finding that second derivative and the first derivative. Very important, you can find the second derivative. That'll show up on the AP test. Questions 6 and 7 are writing tangent lines. And then questions 8, 9, 10, horizontal, vertical, tangency. So 6 through 10 is honestly the things we did on Friday. And then there's the back. It'll show me the back on the back. Now, you don't have to find any areas. That would be an integral. But, yeah, don't even worry about the back. So the front. Your web assigned tonight will have your areas of increase, areas of decrease, areas of concave up, areas of concave down questions as well. Email me if you have.